Hello and welcome to all students. In this lecture, we learn about inner product spaces, and today we are going to solve some examples on inner product of two vectors. Okay, so let us write some examples. Examples. So let us write question number 1. We are solving some problems. Question number 1. Consider the vectors u and v in an Euclidean inner product space. Consider the vectors u and v in an Euclidean inner product space. Euclidean inner product space and compute inner product of u v inner product of u v. Okay, so in the first case, vector u is given to be 1 comma 1 comma 3, and vector v is given to be 2 minus 2 7. Okay, so let us, and in the second case, u vector is equal to 1 minus 1 6 2, 1 minus 1 6 2, and vector v is equal to 6 6 6 7 4. Okay, and we have to compute the inner product of these vectors. Okay, so let us write the answer. Let us write the answer. Okay, first, vector u is equal to 1 comma 1 comma 3, and vector v is equal to 2 minus 2 7. The inner product space is Euclidean inner product space, therefore the inner product of vector u with vector v is nothing but the dot product of these two vectors, so u dot v. So vector u is 1 1 3 dot product with vector 2 minus 2 7. Okay, and we know that how to take the dot product of these two vectors: 1 into 2 plus 1 into minus 2 plus 3 into 7, and it is equal to 2 minus 2 plus 21, it is equal to 21. So inner product of vector u with vector v is 21, is 21. Okay, now let us go to the next. Let us go to the second problem. Vector u is equal to 1 comma minus 1 comma 6 comma 2. Okay, and vector v is given. Vector v is 6 comma 6 comma 7 comma 4. Okay, so now we take the inner product of vector u with vector v, and it is equal to u dot v, as Euclidean space is given. So inner product of two vectors is nothing but the dot product of these two vectors, and the first vector is 1 comma minus 1 comma 6 comma 2, and dot product with the second vector is 6 comma 6 comma 7 comma 4. Okay, and the dot product is 1 into 6 minus, okay, minus 1 into 6 plus 6 into 7 plus 2 into 4. Okay, it is equal to 6 into minus 6 plus 42 plus 8, it is equal to 50. Okay, so inner product of vector u with vector v is equal to 50. So thus question 1 is over. Okay, now let us take the question number 2. Let us take the question number 2. Question 2. Question 2 says that check whether the following vectors are orthogonal. Check whether the following vectors are orthogonal in R4. So Euclidean inner product space R4 is given in R4. Okay, so in the first case, vector is given u equal to 1 2 to 1 2 2 1, and vector v is given. Vector v is minus 1 3 0 1. Okay, and to check the orthogonality of these two vectors, we have to find out their inner product. Okay, so we find inner product. So inner product of these two vectors, inner product of vector u with vector v is, in this case, is a dot product, and this dot product is vector u is 1 2 2 1. Dot product with vector v is minus 1 3 0 1, and it is equal to 1 minus 1 plus 2 into 3 plus 2 into 0 plus 1 into 1. it is equal to minus 1 plus 6 plus 0 plus 1. Okay, and so finally answer is 6. Okay, so inner product of u with v is equal to 6. But two vectors are orthogonal if and only if their dot product is 0. Therefore, and this if and only if their inner product is 0 means this inner product is not equal to 0. Therefore, vectors u and v are not orthogonal. Okay, so we know that two vectors are orthogonal if and only if their inner product is 0. But here inner product is not equal to 0 means these two vectors are not orthogonal. Okay, so let us take next now second set of vectors is vector u equal to 1 minus 2 1 minus 1 1 minus 2 1 minus 1, and vector v is equal to minus 5 2 4 3. Now again we check the inner product, whether inner product is 0 or not. If the inner product is 0, then we say that vectors are orthogonal, and if the inner product is not equal to 0, then we say that two vectors are not orthogonal. So let us find the inner product of these two vectors, vector u with vector v. It is equal to u dot v, and it is equal to dot product of these two vectors 1 minus 2 1 minus 1, dot product with minus 5 2 4 3. It is equal to 1 into minus 5 plus minus 2 into 2 plus 1 into 4 plus minus 1 into 3 into 3, and it is equal to minus 5 minus 4 plus 4 minus 3. So this is equal to minus 8, and it is not equal to 0. Therefore, in this case we say that vectors are not orthogonal. U and v are not orthogonal. Okay, now last is third case. Now third case is two vectors are given. Vector u is equal to 2 minus 3 minus 2 minus 2, and vector v is equal to minus 1 comma minus 1 comma minus 1 2. Okay, again we find the dot product of these two vectors, means inner product of u with v is the dot product of uv, and equal to vector u is 2 minus 3 minus 2 minus 2, and dot product with the vector v is minus 1 minus 1 minus 1 2. okay, and it is equal to, the dot product is 2 into minus 1 plus minus 3 into minus 1 plus minus 2 into minus 1 plus minus 2 into 2, and it is equal to minus 2 plus 4 plus 3 minus 4. So here again we have dot product is equal to 1 and it is not equal to 0, and here also the vectors u and v, therefore u and v are again not orthogonal, not orthogonal. Okay, question number 3. Okay, not orthogonal. Now let us go to the question number 3 now. Okay, let us go to the question number 3. Question number 3 says that find, what we have to find here is find norm of vector u, comma norm of vector v, okay, and we have to find the distance between vector u and vector v. Okay, so first set of vectors is given. Vector u is equal to 2 minus 1 5. Vector v is equal to minus 1 3 4. Okay, so now let us write the answer of this question. Okay, so let us write the answer of this question now. So first of all we find the norm of vector u, and norm of vector u is nothing but the inner product of u with u and raised to the power 1/2. Okay, so it is equal to inner product of u with u means dot product of u with u and raised to the power 1/2 means square root. Okay, and it is equal to square root of u dot u means vector u, dot product of u with u is 2 into 2 plus minus 1 into minus 1 plus 5 into 5. Okay, it is equal to square root of square root of 1 minute. So it is equal to square root of 4 plus 1 plus 25, and it is equal to again into the square root of here it is 30. Okay, so norm of vector u is equal to 30. So this is vector u and norm of vector u is 30. Norm of this vector. Norm of vector u is equal to 30, square root 30. Now we find the norm of vector v. Now norm of vector v is equal to, we can directly write square root of u, square root of v dot v, v dot v. So dot product of vector v. Now vector v is known to you. We write the dot product. It is minus 1 into minus 1 plus 3 into 3 plus 4 into 4, and it is equal to square root of 1 plus 9 plus 16. Okay, and it is equal to square root of 26. So norm of vector v is equal to 26. Okay, now we find the distance between, distance between vector u and v, and it is nothing but equal to, it is norm of u minus v and equal to norm of vector u is 2 minus 1 5 minus vector v is minus 1 3 4. Okay, and it is equal to norm of vector 2 minus minus 1 is 3, minus 1 minus minus 3 is minus 4, 5 minus 4 is 1. Okay, find norm of this vector, and it is equal to square root of dot product with itself is 3 square plus minus 4 square plus 1 square. It is equal to square root of 9 plus 16 plus 1, and it is equal to square root of 25. Square root of 25. Okay. So question number 4. Is square root of 26. Okay, square root of 26. So this is the distance between u and v vector. Hmm. 26. Now let us go to the next question. Okay, now let us, our remaining questions we solve in the next lecture. Okay, so let us stop here. So this is the end, of this lecture. Thank you.